Good afternoon, everyone. Thank you for joining us as we discuss a new approach to asphalt pavement design. This webinar is proudly brought to you by the National Asset Centre of Excellence, or NACOE for short, in partnership with ARB Group, TMR and APA. My name is Angela Ratz and I will moderate this session and provide technical support if required. Being recorded, and the recording and slides will be shared with you once the webinar has concluded. We'd be delighted to address any questions along the way, so please type those into the questions box or the chat at any stage of the presentation and we'll try to get to them at the scheduled break time. We do have a lot of material to squeeze in today, ladies and gents, and so if we don't get to your question, please feel free to contact our presenters after the session. Now, it's with great pleasure that I introduce our speakers for this session, all of whom join us remotely from Queensland. Firstly, please welcome Peter Bryant of TMR. Peter has some 20 years engineering experience in private and public sectors, both in Australia and abroad. Peter is currently the Principal Pavement Design Engineer at TMR. Welcome, Peter. At the time of the work presented in this webinar, Eric Denneman was leading the ARB Pavement Technology and Asset Management team in Brisbane. He has since joined APA as Director of Technology and Leadership. Eric specialises in performance-based design and specification of asphalt materials and the development of design procedures for asphalt and concrete pavements. Hello, Eric. And finally, please join me in welcoming Dr. Jeffrey Lee, a Principal Pavements Engineer from the Pavement Technology team at ARB Group. He has over 18 years experience in the design and assessment of pavements for urban and rural highways, industrial and airfield environments. Thank you all three of you for your time and effort in preparing today's material, and I will now hand over officially to Peter to tell us a little bit more about what we can expect to learn in this webinar. Thank you, Peter.
Thanks, Angela, and welcome to everyone to this webinar on a new approach to asphalt pavement design in Queensland. A lot of asphalt pavement design related research has been undertaken in recent years, including by Austroads, the National Asset Centre of Excellence and the Australian Asphalt Pavement Association, with the key relevant projects listed here. The research has generally shared common goals, which are to reduce the cost of asphalt pavements and achieve value for money, and generally improve the pavement design process to better match field performance. And there has been many linkages between these projects, as well as linkages to international research, in particular in the US and Europe. This webinar is brought to you by the NACOE P10 and P39 projects. The P10 and P39 projects, as well as covering their own unique parts of the overall asphalt pavement design puzzle, have done what none of the other projects have yet done, and that's bring all the relevant parts of these projects together. And that's the draft technical note that we are now releasing to our internal and external stakeholders for input prior to it being finalised. We have run some longer sessions with stakeholders explaining the changes in quite a bit of detail. This webinar today is a condensed version of those presentations and is aimed at providing an overview of the changes. While it's anticipated that many aspects of the new procedures will eventually go into the Austroads guide, in TMR we are keen to reap the rewards of this research as soon as possible, which is why we have developed this technical note. The draft technical note can be summarised into four main changes compared to current pavement design procedures. The first main change proposed is defining the asphalt design modulus through the use of a flexural modulus master curve. Eric will cover this aspect in a moment. The second main change proposed is to allow the use of a mix-specific fatigue relationship in pavement design, which would be done in conjunction with the mix-specific modulus. And Eric will also cover this change and the background behind it in more detail shortly. These first two changes allow a clear and direct link between asphalt mix design and pavement design. The third main change proposed is an upper limit on design traffic in asphalt pavements. And Jeffrey will cover this in a bit more detail shortly. And the final main change proposed is a new approach to considering multiple axle group loads, where strains are calculated under every axle in the traffic load distribution rather than under a standard axle, as is the current approach. And I'll tell you a little bit more about that later. As well as benefits in reducing pavement costs, the changes provide a more fundamental design approach with better links between the asphalt mix design and pavement design. Therefore, the proposed changes are ideally suited to the introduction and assessment of innovations, including better engineered mixes like EME2, which is not easily possible with our existing procedures. Why do we want to make these changes in Queensland? In summary, we are implementing research that's identified improvements to the way pavements are designed, which has benefits in reducing costs and encouraging implementation of innovations. This chart demonstrates the progression of typical full-depth asphalt pavement designs in southeast Queensland in recent years, with, in the chart, total asphalt thickness on the vertical axis and the year of the design standard along the horizontal axis. A 30-year design traffic loading of over 150 million ESAs. Using the 2009 pavement design manual, the asphalt thickness would have been about 430 millimetres for a full-depth asphalt pavement. Between 2009 and 2013, there was concern that asphalt thicknesses were not providing value for money, and changes were made in 2013 specifically aimed at reducing asphalt thickness, and that was through the 2013 pavement design supplement. So using the 2013 pavement design supplement, the thickness for this same design example would reduce from 430 mils down to about 370 mils. This technical note introduces further improvements based on more recent research and will bring immediate benefits in justifying a further reduction in asphalt pavement thickness to about 345 mils for this example using current asphalt mixes. The chart also shows further reductions that should come from optimising asphalt mixes for fatigue performance, and that's where I'm going to hand over to Eric, who will elaborate on the mix optimisation aspects.
Thank you, Peter, and good afternoon, everyone. My presentation this afternoon consists of two parts. First, I'll be talking about developing mix-specific flexural modulus master curves for use in pavement design. And then the second part of the presentation will be presenting the mix-specific fatigue models that we can develop under this tech note. This presentation will get very technical very quickly. Key messages that I would like everyone to take away from this. First of all is that what we're proposing here fits very well within our current design framework, be it Ostro's or the TMR supplement. And the second message is it may seem like a lot of additional testing to be performed in the laboratory, but in reality it's really not that more. We're talking about a couple additional tests compared to the testing that you would do for a high-performance mix design such as EME. So the additional work that needs to be done is actually quite limited. Okay, so with that I'll start my presentation. So let's first recap what we used to do. So within the current Ostro's design framework and the TMR supplement resilient modulus testing. So we do a resilient modulus test at one temperature and one load frequency, and then we use the Ostro's equations to predict from that one test result the flexural modulus of the material at a range of different temperatures and loading speeds. So that's what we're currently doing. So the important thing there is that we're testing in a single condition. what we're proposing to be doing in the future is run flexural modulus test in a 4-point bending setup as shown on the left hand side of this slide, and we'll be testing at different temperatures and different load frequencies to get results as shown on the right. So the graph on the right shows results obtained at different temperatures from the flexural modulus test. So every marker, so there's different color markers there. The markers at the bottom are from tests run at 40 degrees C and different frequencies. Then just above it is the results at 30 degrees C, different frequencies, and so on until 0 degrees. So we run a set of frequency tests at every temperature, and then once we have those results, so once we've characterized the materials over a range of temperature and frequencies, we shift those results in the frequency space to form a continuous master curve. And by doing that shift, we then have the relationship between temperature and frequency, and we can convert between the two, and we can use this master curve to predict the design modulus at any combination of temperature and load frequency. So that is the master curve in a nutshell. I'll be going through the construction of it a little bit later, although not in much detail. So if you lose track, don't worry, the test method explains exactly in the deck note as well, explain exactly the steps that are involved in this. So why were we doing that? Well, so first of all, if you compare this to what we have been doing, is we're running the tests over a range of temperature and frequency, and therefore we're better characterizing the material. And the master curve better represents the flexural modulus over a range of temperatures and frequencies compared to our current method. Well, this will also result in a higher modulus at elevated temperatures, and that's mainly because our current Ostrow's method underpredicts the modulus at high temperatures and low frequencies, which is obviously very important for a warm climate like in Queensland. And we also get more realistic values at low temperatures, as I will be showing on the next slide. So this is an important slide. It basically compares the relationship between frequency and modulus as predicted by Ostrow's versus what an actual measured flexural master curve would give you. So the markers that you see in about the middle of the slide represent the resilient modulus results that you would get for different mixes. So shown here is an EME2, a DG28HM, and an AC10 with some rep in it, the EME2 being the top one. So we do a resilient modulus test, and we can get 1 point, and then from that we predict the modulus at different temperature and frequencies using the Ostrow's equation. So if we use the Ostrow's method, that results in a straight line. So the straight lines on this chart represent the Ostrow's method. Because this is a log scale, it comes with a straight line. The actual measured flexural modulus, the flexural modulus that we've measured in the laboratory is also shown on the graph. Those are the dashed lines. And as you can see, on the left of the graph, that is the high temperature and low load frequency domain. The modulus values that we'll get from the actual measured flexural modulus are higher than what's currently predicted in Ostrow's. And that in turn, of course, will result in thinner pavements when we're using those more realistic values. So that brings us to why we're doing it. These higher moduli lead to reduced pavement thicknesses, especially in climates like Queensland. The mix-specific master curves open doors to innovation. So instead of assuming a relationship between temperature and modulus, we can now actually test it, and that means that people can optimize their mixes to get a better outcome. And finally, I believe that this reduces risk, because instead of taking a measurement at a single temperature and single load frequency, we're now characterizing the material over a wider range of temperatures and frequencies, and therefore have a better understanding of the resilient response of the material in different combinations of it. So we have a much better characterization of the material than we used to have with these mix-specific models. Well, first of all, the basis for the Ostrow or modulus in the Ostrow's design guide has always been the flexural modulus. it says that the flexural modulus in the Ostrode guide is estimated from a resilient modulus value. And the reason why Ostrode uses flexural modulus is because it's based on the Shell design method from 1978, which also used the flexural modulus. And some of the people listening out there may be familiar with the Shell nomographs, which can be used to predict modulus from binder properties. Those nomographs are actually also based on flexural modulus value. So use of the flexural modulus is completely consistent with our current design method. And I recently, an Ostrode project that we've recently completed also recommends the use of flexural modulus master curve, much the same way as we've just discussed here, as the basis for design within the Ostrode's guide. So we're just implementing it early, as it were. That brings me to the test method. For those of you not familiar with the 4-point bending test method, all it is we produce an asphalt beam in the laboratory. We hold it at the ends, and then we introduce a sinusoidal displacement load on the inner clamps and measure the modulus at a low strain value. The test method that we'll be using is the recently introduced AGP T274, which replaces the earlier AGP T233 that you may be familiar with. There were some changes required because we need to be measuring the modulus at small strain. The previous test method really was for the AGP T233 is really a fatigue test method. That means that you're applying from the first load repetition, and that's really not what you want to be doing in modulus testing. We want to be doing modulus testing in a strain range where you're not imparting any damage on the sample, so that's why we need to change that. It also got procedures to do that temperature and frequency sweep. We'll be using a sinusoidal wave shape instead of the Haversine wave shape that's used in T233, and why that's important I'll get to when we get to the fatigue testing. And finally, it includes a procedure to construct these complex modulus master curves. Now, I'm not going to go into detail of what the complex modulus is exactly. I just want to give a quick summary of it, because you may have heard about this talk about dynamic modulus or complex modulus, and you might be wondering how that compares to resilient modulus and flexural stiffness as measured with T233. Well, the real difference between complex modulus and those other moduli is that complex modulus includes the viscous behavior of the material. So we take into account the time lag between the maximum strain in the experiment and the maximum stress. The triangle on the right, I've tried to show that so we've got the maximum strain and the maximum stress, and the time lag is what we call the phase angle, shown in the figure on the right. E1 is the elastic component of the modulus, E2 is the viscous component of the modulus, and combined they represent the complex modulus. The value of the complex modulus is actually not that much different for normal mixes than the normal temperature frequency range than the flexural stiffness. However, it's not the same, and therefore, well, we'll be using this, and that's basically the difference. Brings me to the test method. So on the test method, if we're developing a master curve for pavement design, we want to do a temperature and frequency sweep over as wide a range of temperatures and frequencies as possible. How wide that range is will be predominantly a function of your equipment. So depending on the temperature cabinet, you can stabilize, well, the range of temperatures that you can achieve will depend on your temperature cabinet, and the range of frequencies that you can achieve in the test where you can have a robust load signal will depend on whether you're using pneumatic or hydraulic equipment. Hydraulic equipment typically is capable of imparting load signals at a much higher frequencies than pneumatic equipment, but both can be used for this test method. That brings me to the master curve construction, and I'll just quickly summarize how that works. So, as I said earlier, you run tests over a range of frequencies at each temperature, and then we take those results and we shift them in the frequency space to form a single curve as shown in this figure. And we're fitting that data to a sigmoidal model. Now there are other models available from literature. The reason why we went for this model is that it's used in the American Mechanistic Empirical Design Guide as well as the Californian Mechanistic Empirical Design Guide. That's the only reason. Other models are also suitable, but we chose this one. They all give a similar answer. So the sigmoidal model is shown there. Then the shift of the different frequencies, so the shift in the frequency domain is done by using the reduced frequency and changing the frequency in the test to the reduced frequency with the temperature shift factor. The temperature shift factor is again fitted to the data. So the crux to doing the master curve construction is solving the regression parameters in these different equations at the same time, and that can be done in an Excel spreadsheet using the Microsoft Solver function in it, and it's quite straightforward to do that. But I'm not going to go into that at the moment. Right, then if we have done that for different mixes, we'll get different outcomes. So this slide shows you mix-specific modulus master curves for different mixes tested as part of the TMR research program. The top line are the results for an EME2, and as you can see, that mix has by far the highest modulus, especially at the higher temperatures, and the turtle represents slow-moving loads. So on the left part of the graph, you can see the high temperature slow-moving load space. EME2 has got the highest modulus, and then the DG14HS, which is a mix with a polymer-modified binder in it, has got the lowest modulus of the lot.
So Eric, can you just explain how you get the design modulus, say for a certain traffic speed and temperature from that master curve?
Yes, well that is very much the same as we currently do with those relationships in Ostro's. So we calculate the frequency under the traffic speed using the current Ostro's equation to do that, and you set in your master curve equation the temperature to the to your design temperature, the weighted mean annual pavement temperature, and then the modulus value that you get, you then correct for the design air voids content that you're looking for.
Okay, thanks.
Thanks for the question, Peter. What we can also do is incorporate default values. So the current TMR design supplement has got default values for different mixes, and what we have done is we've converted those correction factors in Ostro's for temperature and load frequency. You can convert those into a master curve. So the graph on the right shows you if you take those two Ostro's correction factors for temperature and load frequency, you can come up with a master curve to cover them both, and you can still use resilient modulus results and then put those values into a master curve. Obviously, the results you're going to get are not more accurate than in the current Ostro's method. The main difference is that you can consistently use master curves instead of the other or the resilient modulus results. So this is a table in the design supplement showing you the default master curve parameters for the different mixes, typical mixes used by TMR, as shown in the left column, and it gives you default master curve values for this. But obviously, this will just end up with the normal Ostro's relationship, as I've shown on the previous slide. But it can be used with default values as well. We have time for questions at this stage.
Brilliant. Thank you, Eric. Well, would you believe we've got a very quiet audience today, and I'm going to assume that's because everyone is tracking very well with everything that you've talked about thus far. But I have typed a note into the chat for our audience to please let us know how you're travelling with the material presented so far. you know, is it making sense? Do you have any reflections or any observations you'd like to share with us? Please do. I'll also take this moment to reiterate that we are recording today's session and all of the material will be made available. So please don't worry too much about writing notes or formulas or anything like that. You'll be able to recap at the end of the session. So Eric, I might hand back over to you, as I believe you're covering the next session also on mix-specific fatigue model. Am I right?
That's correct, and that's a slightly shorter session. So, but it's just as technical. Okay, so again, so this is about developing mix-specific fatigue models. So instead of using the general model that is currently in the Osterode method, we'll be developing fatigue prediction models that are mix-specific. So this slide shows the current Osterode equation that you will be familiar with, which basically says that the fatigue performance of a mix in the field, or the number of cycles to failure, is a function of the volume of binder, the modulus, to take into account any changes in temperature and loading speed, and the strain level at the bottom of the asphalt layer. You'll notice that that is very similar to the shell equation that is shown at the bottom of the page, which is based on, actually it's exactly the same. So that shell equation was developed, it's a laboratory model, it represents the mean performance of 12 mixes tested in the 1970s in Europe, based on mixes from different countries, but all overseas mixes, none from Australia. So this part, the last part of the Osterode equation and the shell fatigue relationship are the same. They provide exactly the same outcome. So the shell laboratory model is currently used in the Osterode fatigue equation, and all we do is we have a shift factor to shift the laboratory performance to field performance. Now you could argue that you could replace that general laboratory model, which was developed again on 12 mixes in the 1970s. You could replace that mean laboratory performance model with a mix-specific model and use it in exactly the same way. So that's what we'll be doing, is we'll be running tests in 4-point bending setup. We'll be testing at different temperatures, and then we fit a single model to those tests at different temperatures, and we'll be making the fatigue performance a function of the modulus of the material again, to account for the effective temperature and load frequency. Why will we be doing that? Well, we want to encourage the use and development of mixes with superior fatigue performance, and think, for instance, of EME2. Mix-specific fatigue models also open the doors to innovation, so it will now be possible to develop your own mixes with superior fatigue performance and characterize them and use them directly in pavement design, which then, of course, hopefully will again lead to reduced pavement thickness, and as a result save the taxpayer money. And in my opinion, this will again reduce risk, because instead of using a general model that was based on the mean performance of 12 mixes tested overseas, we will now be using models that were specifically developed for Australian mixes. And this is another slide on why we were doing that. Actually, the whole reason why we started this project is because according to the current Osterode design method, as the temperature goes up, you need more asphalt to get the same fatigue performance. This graph shows the design thicknesses for a certain design situation using the TMR supplement, so that's the continuous line, at different temperatures. And you will see that in Brisbane you will need a thicker pavement than in Melbourne to carry the same traffic if you use the current TMR supplement. If, however, you use a mix-specific model, and this is a mix-specific modulus and a mix-specific fatigue model, that's not necessarily the case, because the fatigue model especially is more temperature sensitive. And as you can see here, for one of the mixes that we tested under the TMR research program, if we do the design based on using those models, we actually do not end up with a thicker pavement in Brisbane than in Melbourne, which would make us very happy. And the Queensland taxpayer as well. Okay, so again, taking a step back, and the reasoning why we argue that we can do this within our current design framework is that the design method in the Oslo's Guide to Pavement Technology uses the Shell 1978 laboratory model to characterize the fatigue performance of asphalt mixes. That laboratory model is based on the mean performance of 12 mixes. And provided that we use suitable test conditions that are similar to what Shell used, the general model can be replaced with a mix-specific model. And to allow that, we did need to make changes to the test method, and that is one of the reasons why T233 was replaced with T274. And changes in terms of fatigue testing include that we'll now be testing with a sinusoidal wave shape instead of the Haversine, and the reason for that is that Haversine wave shape that we used to use in T233 in effect resulted in a sinusoidal wave of half the intended amplitude, and therefore you would draw completely the wrong conclusions if you would be interpreting that data. We'd be testing a minimum of 18 specimens per result, and if we're testing a different temperature, we'll actually be testing slightly more. We'll be discussing a bit later. And there's also improvements to general calculation and engineering properties that I don't have time to go into. But just for clarity, the results that you may have for mixes historically used from T233 cannot be used in this current tech note. You have to be testing in accordance with T274. Okay, then for tests to develop mix-specific fatigue models in accordance with the tech note, we need to test 27 beams equally divided over 3 temperatures, 9 beams per temperature, and so that's at 10, 20, and 30 degrees C, and that will give us enough statistical confidence to fit our model to the data. The model that we'll be fitting looks like this. It's slightly different from the Shell model. The Shell model was basically a 3-parameter model. This is a 5-parameter model. And the reason for using this model instead of the Shell type model is that it's more sensitive to temperature changes. And you'll basically be fitting this model to your fatigue data and solving it for the 5 different regression parameters that C1 to C5 to come up with a mix-specific laboratory model. So then once we've got that laboratory model, we need to predict field performance from that, and that we'll be doing using the same reliability factor. So all we're doing here is replacing the Shell general laboratory model for mean performance of 12 mixes with a mix-specific laboratory model, and we're using the same laboratory to field shift factor to predict from that laboratory performance to field performance. Thank you. Over to Jeffrey.
Thank you, Eric, and good afternoon, everyone. My name is, again, Jeffrey Lee from Up Group. In my part of the presentation, I'll discuss a upper limit that we propose to put for Queensland. Some of the background, without going into too much details, the idea behind putting a design limit on our pavement is that evidence, both in Australia and overseas is suggesting that right now in the current method we keep on increasing the asphalt thickness, as the design traffic increases, but there have been many observations that when the asphalt thickness gets to a certain point, then really we're not getting a lot of benefit. And whenever we are discussing this concept, inevitably you hear this fatigue entrance limit topics, and in here I basically list out some of the key studies that have been done both nationally and internationally. So for those audience that's keen to read up, you got the reference. But in short, right, basically the first two study was done in the U.S. And they were looking into the fatigue engines limit via laboratory testing. The third one it was done by TRL UK, so they were looking at a lot of the field performance of full depth asphalt pavements that they have there. And in Australia, back in 2009, there's a Oslo report, APT 131, so that was published, which looks at the concept of the fatigue engines limit. And in more recent years, Australian Asphalt Pavement Association has presented a design methodology on long life pavement, short for AP, Asphalt Pavement Solution for Life. And at the moment, there's like a ongoing Oslo project TT2044, which is again reviewing the concept of the FEL and looking at possible options for implementation in the next revision of the Oslo Guides to Pavement Technology. But one of the messages I want to bring out is that there have been a number of studies going on, but right now there's no unique consensus on the method that has been arrived. So since we are looking at how to implement that in Queensland, I will go into a little bit deeper the studies that have been done in Australia. This slide basically shows the fatigue engines limit that is proposed by the APA method. And in short, the design is to come up with different asphalt thicknesses that when we are evaluating at the winter, summer, or the WMAPT temperatures, the calculated critical strain at the bottom of the asphalt is lower than this fatigue engines limit that is proposed, and the method suggests that if that is achieved, then we will have a very long life pavement. And as I've mentioned previously, that there's this Oslo TT2044 project that is ongoing, and in June 2016, that there's a discussion paper titled "Asphalt Fatigue Engines Limits: Guide to Implementation Options" that was presented, and again in short, in there, other than providing a review of the APA method proposed, there's 5 options being presented, to look at possible ways of incorporating in the next Oslo Guide to Pavement Technologies. So in short, right now the most probable options that we can readily implement in Queensland would be option D. Basically, without specifically looking into fatigue engines limit, we are capping the design traffic in our solutions. And in here, just for illustrative purpose, I've put in the full depth asphalt design profile. So in there we have the AC14 with class 320 binder at the top, and a typical AC20 class 600 as the base, and then followed by an improved layer, or which is basically a lightly cemented granular layer, and then putting different design subgrade 5, 7, and 12 into these design examples, so we can have some thickness, to look at. It's important to realize that in this technical note that we are presenting, for pavement that we expect to last very long, we really need to have a very good foundations, and therefore in the technical note, we require that there needs to be a improved layer, as well as any additional select fill if required, so that the top of the improved layer has at least a minimum of 150 MPa. So the asphalt block at the top would have a good support. and with that example, but basically at 200 million easels, I'm proposing to cap off the asphalt thickness at that traffic, and this limit has been particularly considering the southeast Queensland temperatures, because for thick pavement that we are looking at here, most of them would be sitting in the southeast corner in Queensland, within the state. And one thing to notice that this 200 million easel is consistent with the current discussion in a TT2044, which recommends that for the WMAPT between 26 to 34 degree, that they're also suggesting a 200 million easels as the cap. And if we put in the thickness calculated by the upper method, all these are quite comparable. And that concludes my part of that, and I'll hand over to Peter. Before that, any questions, I'm happy to answer.
Thank you, Jeffrey. We did receive a number of questions. They did come through a little bit earlier when Eric was doing the last section. I'll send through one question now. We might save the rest till the end just to keep on track with the time. This one came through from Sandra from the Gold Coast, and the question reads, how easy is the material to lay, and what are the pavement layer sizes? So again, that was in reference to Eric's bit a little bit earlier.
Well, so these methods are they're meant to be used with any type of asphalt. I can maybe Sandra means EME2, which is one of the materials that would definitely be of interest to be used in this framework. EME2 is very easy to lay and very workable. That is what experience overseas has shown, and experience here as well. But maybe I understand the question wrong.
Well, Sandra, if you and your team can let us know if that's clarified it better, or if you'd like further clarification, that would be, just pop it into the chat for us, and I'll send it through to Eric. Maybe we'll move on to the next section for the moment to make some segue, as we're short of time. And I believe this next section is over to Peter. So improved consideration of multiple axle group loads.
Yeah, thanks, Angela. Yeah, so the final change proposed in the technical notes, it's a slightly different topic to the asphalt that we've been hearing about, and the change is to adopt an improved method for the consideration of heavy vehicle axle group loads in the thickness design process. In about 2010, Austroads recognised the need to improve the way axle group loads are modelled in assessing their influence on pavement performance, and at the time commenced a significant research effort on the issue. So the research that I'm talking about here was undertaken by Dr. Michael Moffat from our group under Austroads project TT1614, and there's a number of Austroads reports available from the Austroads website if you would like further information. One of the most significant outcomes from Michael's research was a recommendation to calculate strains under each axle within the axle load distribution, to replace the current approach where strains are only calculated under standard axles. In the current Austroads method, all loads in the traffic load distribution are converted to a number of standard axle repetitions that are assumed to cause the same pavement damage as the actual traffic, and that conversion is done using what are called standard loads. The standard loads are based on peak surface deflection for different axle group types being the same as under a standard axle. So that means that axle groups causing the same surface deflection are assumed to cause the same pavement damage. However, Michael Moffat's research demonstrated that the standard load varies with pavement structure in bound pavements. The use of deflection as an indicator of damage of bound materials is therefore questionable. The research recommended that pavement damage should separately consider each axle load and group within the traffic load distribution by calculating strains under each individual axle without any conversion to standard axles. So we're proposing to introduce this new method for the assessment of asphalt fatigue damage in conjunction with the other changes that Eric and Jeffrey have covered. So this now leads me to briefly describing the new method. The method's fully detailed in the technical note, and there's also a worked example in the technical note for a full depth asphalt pavement. The first step is quite simply defining the pavement structure, including the material inputs to be used, so that's no different to what we currently do. The second step is in two parts, and this is the method for determining the strains under each individual axle in the traffic load distribution. So firstly, the designer calculates the critical strains in the asphalt under both a single axle with single tyres and a single axle with dual tyres. This still only requires a one circular run, except now with two load types rather than one. And the tech note defines the axle loads, tyre spacings and contact stresses to use. Then in step 2, the strains from step 2A, they're linearly scaled to give the strains at all load levels. And linear scaling is possible because the Ostrode's method is based on a linear elastic model where strains are linearly proportional to the applied load. This slide shows how the linear scaling of strains works. The chart plots the strain, the microstrain in the asphalt versus the load level. The orange crosses are the output strains from circularly, determined under a single axle with single tyres at 53 kilonewtons and a single axle with dual tyres at 80 kilonewtons. By drawing a straight line through these points, it's possible to determine the strain at all load levels with no need to rerun any further calculations in circularly at these different load levels. So for example, for a single axle with dual tyres, which is the bottom dash line, at a load level of 40 kilonewtons, which is half the 80 kilonewtons that was used in circularly, the strain is also half. So it's about 53 microstrain, just reading off that dash line, which is half the 106 microstrain. So in our calculations, we'll end up with a table that looks something like this. It's a table of strains for every combination of load level and axle group type. And just remembering, these are strains under a single individual axle from the group and not the strain under the entire group. The next type, using the strains from the previous page, that's done using either the normal shell relationship from the Ostrode's guide or the mixed specific relationship that Eric discussed. Using the strains under individual axles, the performance equations will give the allowable number of individual axle loads. We actually want the allowable number of axle group loads. So there's an additional term, that 1 divided by n, included in the performance equation to divide the number of axles in the group, which is n, to give the allowable number of axle group loads. And then we can compare that with the design traffic, which is also in terms of the expected number of axle group loads. We repeat this for every combination of axle group type and load level, and that can easily be automated in a spreadsheet. The asphalt fatigue damage is then calculated for each combination of axle group type and load. This is done by dividing the expected repetitions, which is the design traffic, for that combination by the allowable repetitions from step 3. And this is very much the same or similar procedure as what's used in the current Austroads guide for concrete pavements. The total damage is then the sum of all damage for each combination of axle group type and load level. And this must not exceed 1 for the pavement to be acceptable in terms of asphalt fatigue damage. So that completes the assessment of the asphalt fatigue damage part of our design. The other aspect is to consider loss of surface shape, which is often called subgrade deformation. So that also needs to be checked. And I won't go into the details here, but that's all explained in the technical note as well. Which was a motorway in southeast Queensland using the different design standards. This chart shows a similar comparison using the same full depth asphalt pavement structure, but in this case for a wide range of traffic loadings, which are shown along the horizontal axis. The top line, the top diagonal line there, shows the required asphalt thickness using the current 2013 pavement design supplement and Austroads pavement design guide for a full depth asphalt pavement. The middle line then shows the required thickness when the new multiple axle method is used, 100 million ESAs that Jeffrey covered. The difference between the top and the middle lines is the reduction in asphalt thickness that will be able to be realised immediately, and that's even without the mix-specific design approach that Eric's described. Optimising the mixes for fatigue performance will lead to a further reduction in thickness, somewhere below that middle line. And the bottom dashed line there is to illustrate just where that line could be with the right mix. We can also see from this chart that the traffic limit of 200 million ESAs that Jeffrey discussed, if you look at the middle line there, is on the basis of using this new traffic method. So in this case, for this example, giving a thickness of 350 mils of asphalt. The limit would in fact be about 100 million ESAs if we continued to use the current traffic method where we convert traffic loadings into standard axles. So that's to give the same thickness of 350 mils for this example, which you can see from where the top line hits the thickness of 350 millimetres. So the upper limit on traffic, it's best to think of that as being 100 million ESAs, or 1 times 10 to the 8 ESAs using current traffic methods, but that's increased to 200 million, or 2 by 10 to the 8 ESAs using this new multiple axle method to give us the same thickness. So that's a pretty quick fly through of that method, but as I said earlier, there's a lot more detail in the technical notes as well as a work example which fully details the method and also brings in the bits that Eric talked about, the master curve and the mix-specific fatigue relationship all into one example, just to show how it all fits together.
Thank you, Peter. And just with regards to that technical note, will we be sending that out to our listeners also? Or how will
we'll send that out. Yeah, we can send that out at the end of the presentation.
Perfect. Well, I'll take this opportunity before we answer a few questions that came through earlier on to thank Peter, Eric and Jeffrey for their time in presenting today's material and to sharing this new approach with us all, which I'm sure everyone's found very insightful. A couple of questions that came through earlier, so I'll read those out to you. First one's come through from Luca, and Luca's asking, shift factor lab to field is a critical issue for fatigue testing. Is there any specific research program that has been done for Australian asphalt aimed at assessing this shift factor?
The shift, well, that's actually a massive undertaking to look at field data, and we definitely need to make improvements in that space. There is some work underway, but so this can be seen as an interim solution, but it will be something that needs to be addressed in a much wider piece of research. So these are basically the improvements that we can make in our current framework without having to touch the shift factor. I think that's the key.
Great, thank you very much for that question, Luca. Another question here from Michael, and Michael's asking, did you use any polymer modified or epoxy modified binders?
We tested one polymer modified binder as part of this project as well, and there's actually some there's a discussion of the use of so. Long story short, it can be used. The answer is yes, and it can be used within this framework as well, within certain limits. That is. Yes, and I actually think while I'm talking, Peter just mentioned that for the right mix we might be able to reduce thicknesses even further, and I think that is key. The right mix. We need to make sure that we need to manage expectations, because if we test the current mixes are used in Australia, it's unlikely that you would see a massive improvement in fatigue performance and modulus compared to what the current shell method predicts. So we're really talking about engineered materials here that have superior properties that are purposely designed. If asphalt producers go running to the lab and start testing the current mixes, they might be disappointed in terms of the thickness reduction they're going to get.
Yeah, possibly except for the EME2 and the polymer modified binder mixes, where we did find a much better fatigue life prediction than compared to the shell relationship.
Yeah. So this is, in one way of viewing this method is to view it as really getting the maximum out of your EME2 mixes in terms of thickness reduction.
Great, and that question was from Michael again. Thank you, Michael, for engaging with us. Question here from Elena, and Elena's asking, does reducing asphalt thickness also provide reductions in CO2 emissions? If yes, have there been any calculations on potential emission reductions by introducing the new design? Any thoughts on that?
No, well, look, the answer is yes. I mean, if you use less materials, then you're going to use, in general, you're going to have less CO2 reductions. Obviously, it all depends on what kind of material you're using. So there may be additional CO2 in developing some of these products, but in general, the answer is yes. It will lead to a reduction. Have we looked at that in terms of what the CO2 reduction is going to be? No, we have not. It would very well be possible with the greenhouse gas emission calculator instruments that are out there in the marketplace. It can be done, but we haven't.
Thank you, Eric, and thanks, Elena, for that question. We might take one more question in the last minute or so we have for today's session, and that's come through from Esther. Esther's asking, which of these changes do we expect to be incorporated in the Austroads design method, and when?
Well, I think there's a Austroads project at the moment to update Part 2 of the Austroads Guide to Pavement Technology, and that's the deliverable for that, which is a new Part 2, is due the middle of next year. So I think it's around June 2017. I would say it's still ongoing discussions at the Austroads level about which changes will actually go into the Austroads Guide. The most likely ones, I think, is the improved method for considering multiple axle group loads. There's certainly discussion and general agreement, I guess, about the upper limit on design traffic that Eric talked about, so we've been careful to align ourselves with the Austroads directions there. So I'd expect that will go into the Austroads guide. I think the mixed specific modulus and fatigue relationships, it still requires a bit further discussion for a decision to be made at the Austroads level.
Thank you, Peter, for that insight. And Esther, hopefully we've clarified that for you. If not, obviously presenter details are there on your screen and you can touch base with them for a more detailed chat at a later time. Well, that's all we have time for today. According to my clock, it's 3 o'clock here on the East Coast. So thank you so much once again to our presenters, Jeffrey, Eric, Peter, for all of that insight. I enjoyed it thoroughly. I'm sure our audience did too. Thank you for joining us, to our wonderful listeners, for another NACOE webinar. It's been a pleasure having you with us. As this webinar closes down, a survey will pop up on your screen and it will be comprised of just a couple of short questions. So please do tell us how we travelled. We do take our feedback very seriously. So thank you so much and hope to see you again. Have a beautiful afternoon. Bye-bye.